Hello everyone, today we will tell you how to design a gun grip using topology optimization. Our presentation will last approximately 12 minutes, and if you have any questions about the presentation you can ask them at the end. Now let me tell you about the content of our presentation. First of all, we will introduce our project product. Afterwards, we will explain our motivation and purpose in making this project. Why did we choose this project and what did we aim for? After that, we will show you the flowchart of methods we applied. We will share and discuss the outcomes we have reached after the applied methods. As a result of discussion, we will make an evaluation and summary. Finally, we will talk about what can be done to move a project to the next stage. The most important factor when designing gun grip is their cost. Since the price is kept in the foreground, the gun grips that are generally in the market have some flaws. They are unnecessarily large, ergonomics are kept in background, and they are not durable enough. We use topology optimization while designing. Simply, topology optimization is a mathematical technique that optimizes the placement of materials inside a certain region while taking into account boundary or load restrictions. Our motivation is to create the best product we can without considering the cost. To do this, we set our goals to be durable, lightweight, comfortable, manufacturable. After our goals were determined, we did our methodology. As a team, we did primarily research, and as a result of our primary research, we determined our design area, boundary conditions, and loads. After these stages were determined, the parameters were selected. MATLAB topology optimization was done by our friend Barış. Our friend Gökçe made the Fusion 360 topology optimization. If the results were not suitable during the optimizations, parameters were selected again. As a result of optimizations, the optimum design was selected, and our friend Glenn created the Bezier surfaces. Finally, it converted to .STL format. While these were being done, our friend John prepared the report. Now my friend Barış will talk to you through in more detail.
Before the beginning of MATLAB CAD modeling, I would like to explain algorithm behind the general topology code. It starts with the determination of the initial design space, forces, boundary condition, material properties, and topology parameters. After that, algorithm starting to finite element analysis. After that, sensitivity analysis and filtering process. Then optimization is finished, and if it is convergent, we can say that optimal topology has been found. Also note that AMR tried to make high spatial resolution for accurate three-dimensional design to avoid post-processing or interpolation as much as possible. Let's move on to MATLAB CAD modeling. We start with the pre-research phase, and we decided to make a horizontal gun grip that make easier to aim fast and accurate. And we decided to our design space with considering average palm length with considering NASA article. You can see our design space fixed on the top. Also you can see the forces applied y-axis on the upside and forces applied through y and x-axis at the left and right sides. Our design space is 120, 50 and 35 volume. To make our optimization process, we scaled about 1 divided by 4 ratio that you can see the right side. After that, we applied forces. The weight of the M4A1 is 3.52 kilogram, which is 32.3 Newton. We have 510 nodes that applied y-axis. So y-axis force per node equal to 0.0633 Newton. To find x-axis force, we calculate the approximate recoil force as 14 Newton by using Newton's third law of motion with considering mass of bullet velocity and rate of fire of M4A1. We have 210 nodes that apply to x-axis. Therefore, x-axis force per node equal to 0.0633 Newton. Also, as I mentioned before, we fixed our design space at top of the structure. Then we determined our material properties. We use aluminum composite AA6061 that commonly used at gun grips. The material has 1440 gigapascal modulus of elasticity and 0.3 Poisson ratio. Let's move on MATLAB CAD modeling parameters. You can see our final design and parameters of it. We changed some properties to see what happened. Firstly, we decreased Wolfrag to 0.15 from 0.25 and we get uncertain results. Then we decreased penalization to 2 from 3 and discontinuous happened. After that, we changed our minimum to 1.2 from 0.75 and gamma effects began.
After completing the topology optimization step, surface modeling process has been applied to the part. In the surface modeling process, third-order Bezier curves are used. The general equations for bicubic Bezier surface are written in the slide. According to these equations and figure, 4 control vertices that are suitable to enclose the part are chosen to model a Bezier curve. All the chosen control vertices to create Bezier curves are shown in this slide. To surround the part obtained as a result of topology optimization, total of 31 layers are created, and each layer contains 5 Bezier curves. In 3D models, surface continuities are utilized when joining different surfaces. The general equations used in surface continuity are given on the left side. On the right side, the surface modeling of the gun grip design, whose control points were shown in the previous slide, is shown. While selecting the control points, G1 and C1 continuities were utilized where necessary to ensure continuity between surfaces. For this, the continuity equations written on the left side were used. There were some gaps in the model resulting from topology optimization. Normally, the upper surface of the gun grip is contact with the gun to ensure that is attached to it. In order to ensure sufficient contact and fit of the gun grip to the gun, the volumetric spaces can be neglected. In addition, there is an extension at the end of the model. Since gun grip models generally do not have such an extension, it is thought that this part is not needed. As a result, this part was also neglected in surface modeling. After completing the surface modeling, the surfaces were converted to STL format. The MATLAB STL format result is shown on the left side. And on the right side, the parts converted to STL format in MATLAB is fixed through NetFab by using Prusa Slicer program.
With the optimization performed with MATLAB, with the same design area boundary loading conditions, the topology optimization was performed in 3D with Autodesk Fusion 360 program. First of all, the design area was determined and the aluminum material with the closest mechanical properties to the material used in MATLAB was selected. After the determination of the design area and the selection of the material, the optimization steps are carried out. After the determination of the relevant forces and boundary conditions, the topology optimization is performed. The solid part, which reaches its final state by removing unnecessary parts from the result obtained at the end of the optimization, is finally converted into a STL model and brought into a producible form. In order to evaluate different design options, it is aimed to obtain multiple usable designs by changing the possible force, volume fraction, and mesh numbers. In this slide, you can see the same forces but different volume fractions for this specific design. You can see the same forces but different volume fractions in a different design from the previous slide. Another situation encountered while using topology optimization in the Fusion program in this project is that similar topology optimization results can be obtained even if forces of equal magnitude in opposite directions are applied from the different points. In this slide, you can see the same forces and same volume fractions but different mesh size effect on the design. At the same time, since the increase in the number of mesh also increases the computational time, it will be more efficient to calculate and analyze the designs according to the which mesh number. See the final design selected in Fusion topology optimization and it is solid state converted into STL. MATLAB has a large library of mathematical and numerical computation, so it offers many tools for implementing topology optimization algorithms. MATLAB can perform high-performance numerical computation for large and complex topology optimization problems, and may also need software and tools for optimization algorithms and visualization of their results. Fusion, on the other hand, is CAD software and therefore has design and manufacturing tools. And it facilitates the integration of optimized geometry with other design phases. Fusion provides less flexibility in problems that need to be optimized up to MATLAB. As a result of the comparison of the two programs, it has been observed that the design obtained in MATLAB is more suitable for the requirements.
In further work, we may consider all the possible materials for the gun grip, try to optimize mounting style so the grip could be mounted in variety of weapons. Also tries ways to mass manufacture with the manufacturing.